let's do a physics problem. I saw this on Bluesky, you know who you are. And, you know, when I see a problem I like, I'm going to have to do it. I'm going to have to model it. I'm going to do it 2 ways, and it's going to be fun. And I'm going to give you all the code. So the problem had this, like, disk, and it had 3 parts, 3M, 2M, M, and then it exploded, and then into 3 parts, and you wanted to find, I actually don't really saw the picture, and I'm not really sure what the question was, but I'm just going to model it. I want to model this explosion. Okay, so let's first think about what has to be true in an explosion. In particular, if we want momentum to be conserved, because I suspect that's what we want. So let's say that I have these 3 pieces, and let's just draw them as 3 spheres for right now during the explosion. Okay, I'm going to call this A, B, and C, and they all have different masses. But they start with the same velocity, but not the same momentum because they have different masses. Well, what if I calculate some type of force between A and B? And so I put that right here, F A on B. There's some force that A pushes on B, and then there's some force that B pushes back on A. If those 2 forces are equal and opposite, then the change in momentum due to that force for these 2 things will be equal and opposite over the same amount of time, and so that force would be conserving momentum. So if I just put that in there, that'd be fine. But now I have 3 objects in there. Well, now I have to do the same thing with A and C, so I'm going to get a force over here, F A on C, and F C on A. And so again, if those 2 forces are equal and opposite, then momentum would be conserved. And then I just have to do the same thing for the other objects. So I need to calculate equal and opposite forces and all the things. Then I add them all up. It's fine that there's more than one. As long as the forces are equal and opposite, then momentum will be conserved. Now, we could have some kind of complicated way to calculate these forces, or we could just say they're constant in magnitude. I want to make them not constant in direction though, okay? But they could be, right? You could just pick forces, like say that one's pushing that way, I could give it a value, just apply the equal and opposite force over here, and it would work out. But what I'm going to do is to use this model. So here's A and here's B, and I can calculate this vector RA to B. I always get this backwards, so I'm warning you right now. And then I have some constant force FO equals 1 Newton. That's my magnitude. So then the force on A would be FB on A would be this force F0 times the unit vector RAB, because I don't want to have that actual distance. I just want that direction. But now I'm going to make it into a vector. And then A on B would just be the opposite of that. So I can go through all these 3 masses, calculate all those forces, calculate the net forces, and I'll be golden. Okay, so the goal is here, start off with 3 masses, let them move with some constant velocity, have a couple time intervals where that constant force is applied, and we can change that, and then turn the force off. So I'll have basically 3 sections. And then, spoiler alert, after that, we're going to do it for many objects, as many as you want, and in our ball. And it's going to be fun. And it's going to be 3D. It's going to be animated. So let's jump over here to Python. Python, here we go. Okay, my computer's in a weird situation. I didn't put this in the right spot. Now I messed up my camera. Okay, we can fix it. Don't worry. So I have here Python. Let's just start making some things. I need this M, right? M equals, let's just say I'm going to say it's 0.1. I'm not really sure. F0 is, I'm just going to say 1 for right now. I don't know if that's going to work or if that's not going to work. And now I'm just going to make 3 spheres. So my sphere 1, I'll call it S1. It's a sphere, and I want to start it at a position of vector -0.2, -0.2, 0, and I'm going to give it a radius. What did I do before? I can't remember what I gave it a radius of before. I gave it a radius of 0.02. Radius equals 0.02. Okay, and I guess I should give it a color, right? I'm going to do a couple things. Color equals color.cyan, and make trail equals false. So make trail makes the object leave a trail. I have that property in there so I can turn it on later. So what I'm going to do is have the things move, and then once it explodes, then they have the trail. Okay. So that's that. Let's just run it and see what happens, because I always like to run things to make sure. So there's my first object. I just need to make two more. S2 equals sphere. Now this one I'm going to have it shifted off up to the right a little bit. So let's say its position is equal to s1.pos plus the vector. What did I do before? 0.015, 0.015, 0.0150, and this has a radius of, what did I give it? 0.013. So you can pick whatever you want here. And color equals color.yellow, make trail equals false. Run it. So there's my other second sphere. Looking nice, okay. Let's keep going. S3 equals sphere, position equals s1.pos plus vector 0.015, negative 0.015. I want it down a little bit. Did I do this? Yeah. And let's give this one a radius of 0.01, color equals color.red, make trail equals false. Run it. Oh, see, we got an error. Vector requires 3 arguments, and I only gave it 2 right here because I'm a big dummy head. So there's my, see, it's not the same shape, and if you really want to do that shape, you could, but I kind of like the spheres. So that's that. Now I need to give them some properties like mass and stuff like that. So I'm going to say s1.m. So I can give s1.m. It's a property of the s1 object called mass, and this makes it easier to keep track of things. And that one is going to be 3 times m. S2.m equals, what did that have? 2m. And then S3.m equals m. Now for the velocity, I'm going to say they all start off with a velocity vector of 0.1, 0.10. So it's moving up. I put it down in the corner so we could have some, like, you know, good spatial awareness here. I need to have them all have momentums. S1.p equals S1.m times V0. S2.p equals S2.m times V0. S3.p equals S3.m times V0. Okay, let's just go ahead and move our objects along and see that they move the way we'd expect. No explosions. Okay. T equals 0. dt, I'm going to put a dt of 0.001, and I'm not sure why. While t less than 3, rate 1000. So what I'm going to do is just to update the position of all these objects in the same way that I would normally. So s1.pos is s1.pos plus s1.p times dt divided by s1.m, right? s1.p divided by s1.m is the velocity. And then I'm going to do the same thing for the other two. s2.pos, s2.pos, s2.p times dt divided by s2.m, s3.pos equals s3.pos plus s3.p times dt divided by s3.m. Boom! Whoo-ha! Okay, so now let's do t equals t plus dt, and let's see if this thing even runs. Because it might not, you never know. There. Nice. Okay, so now I'm going to define 2 things. TS is the start of the explosion, and TEX is the time of the explosion. And, you know, I'm not sure what the best thing to do is here, but let's just say it explodes after 1 second. So TS equals 1, and TEX equals 3 times dt, so 3 time intervals for the explosion. Okay, so what I need to do is to, that's this first part. So let's do while this is less than TS, and then I'm going to make another loop. While T less than TS plus TEX, right? The explosion start time plus the time of the explosion. Rate 1000. It'll only be 3 time intervals, so it's not a big deal. So the first thing I'm going to do is to calculate these vectors R12. So vector R12 is the vector from 1 to 2. So it's going to be S2.pos, I said 2, .pos minus S1.pos. And then I'm going to do R23 is S3.pos minus S2.pos. I'm going to kind of like a cycle here. And then R31 equals S1.pos minus S3.pos. So I have all my variable R1, R2, and so forth like that. I don't need to calculate all of them. I just need to do, I'm just checking to make sure I did it the same way. Okay. Now I'm going to calculate that force. I'm going to call this F12. It's the force on 2 due to 1. So that's going to be my F0 times norm R12. And you see I have this nice convention here, right? So that I can keep things straight. I think I may have this backwards. I always get things backwards here, but it doesn't matter. You can just fix it at the end. Now I just need to calculate the other force, the other 2 forces, right? I don't need to calculate all 6. I just need to calculate 3 of them. F23 is, I did call that F0, right? Do I even have F0? Yeah. F0 times norm, spell it right, norm R23, and then finally F31 is F0 times norm R31. Now I can calculate the net force on each object and update the momentums. S1.p equals S1.p plus the net force. And it's going to be negative F12. I'm looking at my notes here, so I know that I got that backwards. 3-1, right? So if it starts with 1, no, that's right. If it starts with 1, it's on 2. So the force on 1 would be opposite of that. So that's why there's a negative. That one ends in a 1, so I don't have to have a negative. That's my convention. You could do it manually if you wanted to. It doesn't really matter. And then that's the net force multiplied by dt. S2.p is S2.p plus, and again, I can kind of just figure out what I'm going to do here. So the ones that end in 2 up here, so F12, and then the one that doesn't, it starts right there, minus F23. And then S3.p equals S3.p plus, again, I'm going to look at the ones that end in the 3, so it's F23 minus F31 times dt. So I've updated the momentums. Let's update the positions. S1.pos is S1.pos plus S1.p times dt divided by S1.m. S2.pos is S2.pos plus S2.p times dt divided by S2.m. S3.pos, S3.pos, POS plus S3.p times dt divided by S3.m. And then T equals T plus T. Goodness gracious. Okay. Now, so what I'm going to run this, and it should have them move, and they should start moving away. And then I'm going to turn off the explosion and run the time for more. But let's just see if this stuff works. Something happened. Maybe that worked. Let's do another one of these. So TS is 1. So let's run this down here. Oh, now I'm going to say S1 dot make trail equals true. S2 dot make trail equals true. S3 dot make trail equals true. And then paste this down there, and let's say while t is less than, let's say 4. And so that should be the same. It should work just fine. If there is, they should diverge after the collision then. Yeah. Nice. Let's increase that force just a little bit. Let's make it 2. Okay. There you go. Now, you could print out, and I'm going to print out the final momentums. You could plot it too, but I'm just going to print them. let's print out the final and the initial. So print P1 equals S1.P, and then let's put the units, kilogram meters per second, and then it's going to copy this, do the same thing for P2, P2, P3, P3. So they are going to have different momentums because they have different masses. Then I can just copy this and at the end print it out again. You can print it out right after the explosion or right after this, doesn't really matter. But if you want those values, you could get those values. And there's no right answer, right? Because it could be any number of things that could conserve momentum. It depends on what kind of forces cause that explosion and in what direction. And then there's my final, my initial momentums, final momentums, all great. Okay, that was for 3 masses. Let's do a whole bunch of masses. As many masses as we want. So let's just, I should have started a new program, and I didn't. Okay, start a new program. Oops, this does that sometimes. New trinket, web vPython, visual. I'm gonna, I always do this, print 1. Sometimes if I save it before running it, it gives me multiple copies. Mini ball explosion, save. Okay, so we need to do a bunch of things here. Then the first thing that we're going to do is to make a list of all the balls. Okay, I'm gonna not have ball 1, ball 2, ball 3, but all the balls are gonna be part of a list. So I need to come up with some parameters in that situation for making this list. Let's start off with n equals 5. I still want m equals 1, and I'm gonna make the mass. I need the radius of the whole thing. Let's say, what did I use before? The radius of the whole thing was 0.04, and then I need a starting location. I had that first ball, but I need a starting location. I'll call this r start. It's gonna be the same thing. It's gonna be vector negative 0.2, negative 0.20, and I'm gonna need initial velocity. Same one. v0 equals vector 0.1, 0.10. Okay. So n is the number of balls I'm going to make this into. Oh, I do need this force too. F0. Now, the more balls I have, the lower the total mass. Oh, I do need to change. That was one thing I didn't do. The lower the, no, that's fine. The lower the total mass. And so if I have a lower mass, I need less force pushing them apart because the total force is going to be the same. So let's say this is, what did I use before? I'm going to use 10 divided by n. I just picked 10. But that means that if I have more force, more masses, then that force is going to be less because all the masses are going to have a lower mass. Okay, so let's do this. I'm going to make the list of my balls, I'm going to call it BS for balls. BS is an empty list, and then n equals 0. So what I can do is to go through and add objects to my list until n is equal to n. That's what I'm going to do. While n less than n, so I'm going to first create a random vector for the location of this ball. So RT is going to be equal to R start plus some random amount. And I'm just going to have a randomly distributed over the radius capital R. So that will be R start plus vector. I can do R times the vector 2 times random minus 1. 2 times random minus 1. 2 times random. So random gives us a number between 0 and 1. If I do 2 times random, it gives me a number between 0 and 2. If I subtract 1, now I'll get a number between -1 and 1. So if you think about that starting point, I'm moving in a cube R values in either direction. And so that's how I'm going to put my spheres. I could limit it to an actual spherical distribution, but I'm not going to because I don't have that many balls that really matter. Now I do need to, once I have that, I'm going to also need to calculate the radius. So I'll call this RT, and it's going to be just a radius. This one's a little bit weird, but I'm going to just do the same thing. What did I do for R? The R's. No, that's R. Yeah, same R because it's in the same sphere. So let's just do 2. No, I do not want to do negative radiuses here. That's what I did wrong. So let's just do R times random. That's it. And it's going to be between 0 and capital R. Now I don't want 0 radius balls. Okay, but it'll be fine. Now I'm going to make that sphere. So BS equals BS plus a sphere. The position is going to be equal to RT. The radius is going to be equal to RT. Make trail equals false. And then I need to add 1 to my n. N equals n plus 1. Let's just see what this looks like. So there's my 5 or however many, yeah. And you see some are small, some are big, and they're all stuck together. That's exactly what I want. Now, I do want to set a minimum size, right? So let's do this. Once I calculate RT right there, I'm going to actually move this up here. Let's put that first. Let's calculate RT, capital RT. And if I'm only going to use this value if RT is greater than R over 8. I don't even know, I just picked a number, right? So if it's less than R divided by 8, it's too small, I don't want to include it. So, but if it is that, then I'm going to do all this other stuff, right? So I'm only going to add 1 to my counter if I met my criteria for my random number RT. Let's see what that does. Okay, so they're not right on top of each other, and that's fine, but they are some set size. Okay, looks like we're good. Now what I want to do is to give them all a mass, right? I need to find the mass. Now, one things I can do is to give it a mass proportional to its volume. That'd be kind of fun, so let's do that. Let's say that I have the total mass is 1. I'm going to put that at 0.1. What did I do over here? Okay, that's the reason. Let's put this at 1. Okay, the total mass is 0.1. I'm going to calculate the density of a sphere of radius r. So rho is going to be the mass divided by, let's put the 3 up here. 4/3, 4 times pi times r cubed. So that's the density. Now down here, I can calculate the mass based on the volume of each one. I already have that up here. So let's just say this. MT is my temporary mass. And I have that RT value. So it's going to be rho times 4 times pi times RT cubed divided by 4/3. Yeah, that's right. And then when I make that sphere, I'm going to go over here and add in M equals MT. So now I've already put the mass in as a property of that object. Let's just go down, and after we make that, I'm going to go through the list and give them an initial initial momentum, and which I could do in here, but I don't want to, and initial net force. So for B in BS. So this goes through the list BS and calls each item B. So I can reference it as B and do whatever I want. So, oops, what happened? B.P is the momentum property of that particular version of the list. It's just going to be equal to B.M times V0. So that goes through and sets the initial velocity. B.F is vector 0, 0, 0. What that does, I'm going to call the net force on each item B.F. So I can change that later, but I want to set to something 0. Okay. Now let's just go through and move the objects and make sure they all move in a timely fashion. So I have the same thing I had over here. T equals 0, TS equals 1, DT equals 0.001 tex equals 3 times dt. So I have the same values from before, but I'm going to run this while t is less than 3, rate no explosion, rate 1000. All I'm going to do is I just need to update the position of each object. For b in bs, this is really easy, b.pos equals b.pos plus b.p times dt divided by b.m. And then I need to update time, t equals t plus dt. So let's see if they just all move as a group. I haven't even saved it. Have I saved it? Save. Run. Okay, looks good. They're all moving together like a big happy family. Okay, so now I need to do the explosion. So let's do this while t is less than ts. And then over here, while t is less than ts plus tex, rate 1000. So I need to calculate the force. That's what I need to go through, calculate the force, update the momentum, and do all that stuff. So here's the first thing I'm going to do. I'm going to do a trick, right? Because I want to take each sphere and calculate its vector to the next sphere and use that to calculate the force. But I don't want to do that with each sphere calculating its own vector. It can't push on itself. So here's the trick I'm going to do. For I in range length of BS. So this will go through BS and just say 0, 1, 2, 3, 4. Those would be the I values. I'm going to first set the force to 0. So BS I, that's the ith element, dot F equals vector 0, 0, 0. So it's going to go through, set the force equals 0, because now I can add up the forces due to all the particles, other interactions, and add it to that. Okay. Now for J in range length of BS. So this is a double loop, right? The first thing I want to do is to not use I equals J. So if I is not equal to J, then I can do something. But if they're equal, then just skip over this part. So the first thing I'm going to do is calculate that RT vector, and it is bsj.pos minus bsi.pos. Now I can calculate the force. So bsi.f is bsi.f. I'm adding it to the existing value, right? I'm summing it. So I need to have that initial one plus f, or actually I had minus because they're backwards, minus f0 times norm RT. And that's it. So now I've calculated the force on every single object in that length right there. Now I can go through and update the momentums, update the positions. For B, B in BS. B.P equals B.P plus B.F times ET, B.POS plus B.P times ET divided by B.M. Same as before, and then update time. T equals T plus dt. Now I can go back to my normal way of calculating, but the first thing I want to do is to turn on the trails. So for B in BS, B.make trail equals true. And now I can just go up here and copy this thing, right? They're just going to move with no force again. And let's just say 3. Oh, something happened. I can't find nrom. That's weird. Okay, well, I can fix that. nrom. And it's in 3D. Look at that. I mean, that's pretty cool. And every time you run it, you're going to get something different. But I think I'm pretty happy with this. What if I do 10 10 objects instead of 5. I can just change this to 10. So you get those super tiny masses and they explode all really big. So what you can do is to limit that. That's where that limiting case comes from for the limiting size. Smaller size and smaller mass. So I can just change this to 4, and then it won't get too tiny because those tiny ones just get shot out really fast. That looks pretty good though. Now, if you want to see if momentum is conserved, I'm not going to do it, but you could go through and plot, and that's homework for you. You can pick different values, look at the total momentum as a function of position or function of time. In the x direction, the y direction, the z direction, you could do that for energy too, but of course energy is not going to be conserved, or kinetic energy is not going to be conserved. But I'm pretty happy. Let's do one more thing. I just want to do one more thing. Okay, when I make my balls appear, let's make random colors. Color equals vector random, random. So remember, random is a number between 0 and 1, and color can be described as a vector with the red, green, and blue between 0 and 1s. So it's going to just make a random color, completely random color for each of the objects. It's going to be kind of cool. See? That is way better. Oh, yes. I like it. Okay, there you go. Hope you enjoyed that. That was kind of fun. Code for both of the codes will be down below. You can have them and play with them and do whatever you want with them and have a good time. I'll talk to you later.